So it says find an equation of the tangent plane to the given parametric surface at the specified point. So r of uv has components u sine v, u squared, and 2u cosine v. And the point on the surface is the point you get when you plug in u equals 1 and v equals pi. So right away, I would find that point of tangency, the point where you're going to find the tangent plane, right? So the point where that plane touches the surface is the point of tangency, and it's going to be the point on the surface generated by the values of the parameter u equals 1 and v equals pi. The point of tangency on the surface is going to be given by r of 1 pi. I'm going to write it in component form to emphasize that it really is a point. We're thinking not of the arrow, but of the tip of the arrow here. So when we plug in u equals 1 and v equals pi, what do we get here? What's the sign of pi? Pi. Sine of pi is 0. So we get 0 for the first component, or really the first coordinate of the point of tangency. And then, so notice I didn't bother plugging in u equals 1 because 0 times u is 0. Okay, and then what do we get when we plug in 1 for u for the middle component? Well, 1 squared is 1, right? And then what do we get when we plug in pi and 1 for pi for v and 1 for u? -2, because cosine of pi is -1. So -1 times 2 times 1 is going to be -2. Agreed there? So the point we want, or the point of tangency, is this guy. Okay? All right, so that's good to keep in mind. Now, we've already discussed once tonight, how do you find the equation of a plane? What two things do you need? A point, right? We've got our point, don't we? But you also need a normal vector, right? Okay. So this is where the new stuff comes into play. To get the normal vector, you take RU, cross it with RV, right? Because both RU and RV, the derivative of R with respect to U, the derivative of R with respect to V, both of those are vectors that will lie in the tangent plane if you put, say, their initial point at 0, 1, -2. They will both lie in the tangent plane. So if you cross them, you'll come up with a normal vector to the tangent plane. That's the idea in this one. So that's kind of the connection you had to make to do this one successfully. So, all right, if we want to, so then the first order of business at this point is to find the derivative of R with respect to U. Okay, so what's the derivative of this first component with respect to U? So sine of V, and again, I'm just going to use component form here just for fun. What's the derivative of this second component with respect to U? What is it? So 2U. What's the derivative of this guy with respect to U? 2 cosine V. Does everybody believe that? Okay. And then RV. So the derivative of U sine V with respect to V? U cosine V. The derivative of U squared with respect to V? 0. The derivative of 2U cosine V with respect to V? Minus 2U sine V. Now, you could take RU cross RV as is. Wouldn't it be easier to plug in U equals 1 and V equals pi first and get numerical values for those components? Yes, yes, it definitely would. So if we plug in, oh gosh, I'll do it right here. So if we take the derivative of R with respect to U evaluated at U equals 1 and V equals pi, so what is this, in other words, what does this guy become if you plug in V equals pi and U equals 1? So sine of pi is 0, isn't it? And then 2 times 1, 2. And then 2 cosine v. What's the cosine of pi? So -2. Everybody see where I'm getting at? Okay. And then the derivative of r with respect to v evaluated at 1 pi. Okay, so you got to focus your eyes on this. So u equals 1, v equals pi. So you'd get -1 for the first component. Does everybody see that? And then, well, 0, right? And then -2 times v equals pi. Isn't that 0 also? Okay. Everybody see that? Now, to get our normal vector, now we're back to the first chapter stuff. Take the cross product of RU cross RV both evaluated at 1 pi. And we'll have our normal vector. So this is a true cross product, I, J, K. Let's see, 0, 2, -2, -1, 0, 0. As opposed to the fake cross product represented by the curl, right? Okay, so cross it out. What do we get for our first component? So 0i minus, what do we get for our second component? Yeah, so it would be, okay, minus to begin with, and then you got to be careful here. 0, okay, minus, but that will be a positive 2, right? And then j on the end. So it will be plus 2j when all is said and done. And then what do we get there? For the third component, plus 0 minus a -2, k. So that'll be plus 2k. So 2j plus 2k. Does everybody believe that? Or if you want to stick with the component form, 0, 2, 2, if you prefer. We've got our point. Let me write down our point. The point is 0, 1, -2. And your normal vector is 0, 2, 2. Then we go back to the equation of the plane that you were first introduced to in the very first chapter. A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. A, b, and c is your normal vector, the components of your normal vector. And then, of course, x naught, y naught, z naught, point on the plane. So what do we get here? What happens to this guy? 0. This guy? 2 times y minus 2? Nope. 1. Got to look at the right thing. All right, and then what else do we get? Plus c would be from the normal vector 2. I guess I can point by making it an arrow. Times z minus z naught. So plus 2 minus -2 plus 2, like that, equals 0. And I think one slick way of doing this from here on out then is to divide everything by 2, right? Wouldn't that work? And then you have y minus 1 plus z plus 2 equals 0. So what do you end up with? Y plus z plus 1, but if you move it to the other side, equals -1. Would you buy that? Okay.